Okay, everybody, how are you doing? We have finished covalent bonding, and now we're going to move on to something called ionic bonding. And ionic bonding is a little different. We're still going to have to draw our dot structures, but ionic bonding again is going to be a little different than covalent. It's much simpler because it's kind of a one-dimensional kind of thing. Excuse me. So when we look at ionic bonding, we're going to look at a transfer of electrons this time. So instead of two elements coming together and sharing, because they have both have relatively high electronegativities or electronegativities that are fairly close. When we look at the transfer of electrons, we're going to look at elements that have drastically different electronegativities. And because of that, you're going to get a transfer of electrons from a metal to a nonmetal. And the key is going to be this transfer. All right. And it's always going to be from the metal over to the nonmetal. Okay. This is going to create a plus and minus ion. Okay, and once this creates a plus and minus ion, they're going to attract each other in very strong bonds, okay, over a three-dimensional crystal structure. Okay, both ions are going to have an octet, all right, in this case, okay, which are very, very stable, all right, and the shape of this, or really, there's different crystal shapes. We're not going to go into too much detail in this class on crystal shapes, but you end up getting into a crystal lattice. A lattice is a regular geometric arrangement of ions, and each ionic compound has a specific crystal structure based on the size of the ions, how they fit together, how they attract. So it can get kind of complicated on what this crystal actually is, but you probably remember from earth science that you have different cleavage planes and different types of crystals that you can form. And that has to do with, the type of bonding. So really it's your bonding here that creates this very stable structure, which then has these properties. So, very strong bonds, they're all going to be very hard solids. They're all going to have very high melting points. They're all going to be in a crystal lattice. So it makes ionic bonding much simpler than covalent because you don't have all these different things going on. Okay, something you have to know, really important, is the properties of these, and we'll look at this towards the end, is you can conduct electricity. Okay, so ionic compounds can conduct electricity, but only when ions can move. So they're going to conduct as a liquid, an AQ, and a gas because ions can move. And sometimes we use the term mobile, important that you know this, mobile ions. Okay, so mobile ions is something you really want to do. Mobile means moving ion. So again, in these phases, you can conduct, okay, but not as a solid. All right, important to know, not solid. Okay, and again, we will take this down on a later clip, but just want to let you know that. So you're gonna have to memorize this stuff. Really important. Now, why is because you have the plus and minus, so we'll see how that works. All right, ionic compounds are going to be called salts. Okay, so a nickname for any ionic compound is going to be salt. In fact, they're all called salts. So a little example of this would be sodium chloride, very simple, where your chlorine would be the larger one here, and sodium would be the smaller one, and they would fit together in this kind of arrangement. This is kind of the blown out arrangement, but when you see them here, you'll see in this crystal, you'll see the Cl and the Na tightly fit together where the Na is surrounded by Cl's, and if you look at the Cl, it's surrounded by all Nas. So you really see how ionic compounds, when they're packed together, again, this would be a crystal, okay, a regular arrangement crystal, okay, and very, very strong bonds. Okay, so really that's everything. That's really the inside scoop. How you draw these, we can, again, just like we drew Lewis structures of covalent, we can also draw Lewis structures of ionic. So again, before you do this, you have to decide if I'm non-metallic only, then I'm going to be covalent. If I'm metal and non-metal, okay, that is when I'm going to do my ionic structure. So you have to make that decision first. Okay, so number one, first what we're going to do is we're going to transfer the electrons from the metal to the non-metal with my dots. And I'll show you how to do this. Okay, something you want to keep in mind is make sure that your metals lose all of the electrons and the non-metals gain all the electrons. So the number lost has to equal the number gained. Okay, so gain must equal the loss. Okay, you've heard that 1,000 times before, so that is important to know also. Okay, the metal atom is going to get a positive charge. Okay, the non-metal always gets the 8 dots and a negative. So again, you're talking about dot structures that look much alike and they follow the same rules. So There's no linear, bent, tetrahedral, pyramidal, trigonal, bipyramidal. There's no crazy stuff here. It's really the same kind of way you're doing things. Okay. The metal atom is always written first. Okay. A couple of things to keep in mind. And if you have multiple atoms in a compound, if you have multiple, I should say, ions in a formula, you're going to use coefficient for those multiple ions of each type. Okay. Again, we're going to go through this step by step. So let's just say you had sodium chloride, right? So, calcium chloride. You want to draw the dot structure for this. So the first thing to do is to write your dots. So what I would do first, I would take a calcium, right, and I would have my two valence electrons for calcium, and then I would have my chlorine with my 7, right? Chlorine's going to have 7 dots. I think we're used to doing this now. Okay, so that's fine. Now the key is you're going to transfer all your electrons from metals to nonmetals. So I'm going to transfer my dot over to here, but I got a little bit of a problem because chlorine can't take this extra dot. It can take one of the dots, but it can't take both. But when elements react like this, they must lose all their dots and must gain all dots. So what we're going to do is to solve that problem, we will add another chlorine. And if we add another chlorine, okay, like that, we'll see that this dot can fill the space there. All right, so those dots will fill those spots. All right. All right, so what happens as a result is this, and this is going to be really important, is that the calcium, now because it's lost 2, you're going to become 2 plus. All right, so you can think about this as lose 2, okay? And your chlorines have gained 1 apiece. So this is going to be a negative charge, that's going to be a negative charge, right? And this is going to be a positive. So how we write the dot structure is putting the metal atom here with its charge, make sure you have the charge, and then we're going to take the non-metal atom, and we're always going to have 8 dots around it to simulate that has gained its electrons, right? Now, the key behind this too is the fact that what charge will this be? Well, because each of these guys gained 1, then the charge is 1. Okay, and I'm going to put that in brackets. Okay, and because I have 2 chlorines, again, there's 2 chlorines, that becomes the coefficient that I need here. I'm going to put that in front there. So this becomes the correct dot structure. All right, so it's really very easy. A couple ways you can know you did this right is by looking at the total charge on the negative. 2 times minus 1 is the same as the 2 plus. Okay, very similar to how we did the crisscross, right? We took 2 plus and minus, and we crisscrossed, and what do we get? We get calcium chloride. Now you see why you have calcium 2 chlorides, because you need 2 chlorides to gain the 2 electrons from calcium. All right, so it's important to know that. All right, so again, a way to see that is to do it that way. Again, if I get rid of my ink, you'll see that's the way things work. As far as MgO, okay, we can do it again with MgO. Again, we can see that Mg would have 2 electrons. Oxygen would have, I'll use X's this time so we can see it. Oxygen has 6. This one works kind of nicely, okay, because you can take this electron, move it there, and this electron, move it there. So what we will have is we'll have Mg with a 2 plus, right, because it lost 2, and oxygen has gained 2. So we're going to have oxygen always gets the 8 dots. Remember from up here, you're always getting 8 dots. All right, like I can make them X's. X, 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 dot, X, dot, just to show you where they came from. In parentheses, okay, and have to make sure you put the minus 2, and that's why we have magnesium oxide. A good way to do it is simply crisscross the charges, and you should get the element. All right? And if I want to do aluminum oxide, watch how I could do this very quickly. And then I'll show you, I'll go backwards. If you want to get these things done real quick, here's a little trick, is draw your metal ion, right? Go to the periodic table, get the charge plus 3. Go to the periodic table, get your oxygen charge is minus 2. Give the oxygen 8 dots. All right, you can do that. Okay. Take the subscript from aluminum, multiply aluminum, put your non-metal in brackets like you're supposed to, take the subscript from the non-metal, put it in front, and there is your structure. That's it. So you can just use the formula. All right. How this would work out if you were to draw this out is that, remember, aluminum has 3 dots, Okay, oxygen has 6 dots. So if you transfer a dot over there, that's fine, and a dot over there, that's fine for the oxygen. But if you notice, aluminum's got a leftover dot. So what do? We can draw another oxygen, right? So we draw another oxygen, 6 dots, and then we take this and we move it over. But we have another problem again, right? Because we have an open spot for oxygen. So we draw another aluminum with 3 dots, and we bring a dot over for here, and that's fine for oxygen. But we got another problem because aluminum has 2 dots I didn't use. So I draw another oxygen, and I got to keep going like this until you reach a point where the ions have reached their numbers, the correct numbers, where they get together. So here you go, a dot there, and here you go, a dot there. Okay, and that's why you have 2 ALs for 2 ALs and 3 oxygens, and you remember you have. So you see why things are now working out. When you crisscross, you get that. So it all works, right? And that's why you have Al2O3. That's why nature is Al2O3, because again, you lose what's overall. You lose 6, and overall you gain 6 for the non-metal, right? Electrons. Okay, so that's how you do dot structures for Lewis structures for ionic. That is ionic bonding in a nutshell. So again, it's very easy to do. You just have to practice. And I think the big problem here is knowing the difference between ionic structures and covalent structures when you have to put them all together. All right, so at this point, we'll move on to the last bonding, which is metallic bonding. We'll see that in a different video. Okay, talk to you soon.